Mars can produce dust storms so large they do something that sounds almost absurd. They do not swallow a valley. They do not swallow a country. They do not even stop at a continent. They can swallow the planet. That is not metaphor. And it is not the kind of exaggeration science videos sometimes drift into when they want to make a world sound more dramatic than it really is. On Mars, there are storms that can spread so far and throw so much dust into the air that the surface below begins to disappear behind a thick, light-eating veil for weeks, sometimes for months. And that should sound strange right away, because Mars does not look like a world that should be capable of this. When most people picture the planet, they picture stillness, flat red deserts, scattered rock, a thin atmosphere, a cold horizon, maybe a faint wind moving over a dead landscape. Mars, at a glance, feels like a place where very little happens. It feels empty, dry, almost finished. But that first impression is wrong in a very important way. Mars is not quiet because nothing is happening. Mars is quiet because most of what matters there happens slowly and at enormous scale. A storm can begin the way you might expect. Dust lifting from the ground, a haze on the horizon, a darker smear spreading through the sky. Nothing about that sounds especially alien at first. We know dust storms on Earth. We know what wind can do to dry ground. So the instinct is to file Mars into the same category. Another desert, another storm. Just bigger, maybe. But that comparison breaks down very quickly. Because on Mars, a dust storm is not just weather passing through a landscape. Under the right conditions, it becomes part of a planetary system. It feeds on the atmosphere. It changes how heat moves through the sky. It spreads, deepens, and thickens until sunlight itself starts to fail at reaching the ground. And once that happens, the danger is no longer about wind in the way people usually imagine wind. It becomes a problem of darkness, a problem of power, a problem of survival. This is why the storms matter so much. Any machine we place on Mars has to live under that sky. Rovers, landers, surface instruments, future habitats, communication systems, power systems. Anything that depends on light, on temperature control, on steady contact with orbit, or on the simple assumption that tomorrow will still look roughly like today, has to face the possibility that Mars can turn against it for an entire season of waiting. And if human beings ever want to live there, even briefly, that problem stops being academic. It becomes personal. Because a storm on Mars is not dangerous in the cinematic way people often assume. It is dangerous in a colder way than that. It can isolate. It can starve a system slowly. It can wait out machinery. It can turn a functioning outpost into a sealed pocket of vulnerability under a sky that no longer gives you what you need. And the strangest part is that this does not happen on a world with a thick atmosphere, or a powerful hydrological cycle, or oceans feeding giant weather engines the way they do on Earth. It happens on a world whose atmosphere is so thin that, at first glance, it seems like it should barely be able to carry dust at all. So that is the real mystery. How does a planet with so little air create storms so large that they can erase the planet beneath them? And more importantly, what kind of world is Mars really, if the place we call barren and still has been hiding a climate engine like that the whole time? If this kind of deep space story is why you're here, subscribe and stay with me. We're not just looking at Mars tonight, we're looking at what kind of world it really is. If you follow your instincts, Mars should not be able to do this. That is the heart of the problem. A planet with a thick atmosphere, strong pressure, and a busy weather system, yes, maybe. A planet with oceans, clouds, and a heavy sky, sure. But Mars has almost none of that. Its atmosphere today is a thin remnant, less than 1% of Earth's by volume. It is cold, dry, and bad at holding on to heat. On paper, it does not look like the kind of place that should be able to build a storm big enough to erase itself from view, and yet it does. So the first thing to understand is that modern Mars is not the whole story. The planet did not begin as the world we know now. Long ago, Mars was warmer. Its atmosphere was thicker. Liquid water could move across the surface. It was not Earth, but it was far less hostile than the empty red desert we picture today. Over immense stretches of time, that changed. The atmosphere bled away. The planet dried out. What remained was not just a thinner sky, but a completely different relationship between the ground and the air above it. That shift matters more than it seems, because once Mars lost most of its atmosphere, it also lost one of the most basic stabilizing systems a planet can have. It lost the ability to hold heat well. Here on Earth, even in deserts, the atmosphere still does a lot of work for us. It slows down the rate at which warmth escapes. It softens extremes. It spreads energy around. Mars cannot do that nearly as well. When sunlight hits the ground, the surface can warm up surprisingly fast. But once that energy starts leaking back out, there is very little air overhead to catch it and hold it in place. So the planet swings, and it swings hard. In the warmest part of the Martian day, conditions near the equator can feel almost deceptively mild right at the surface. But move even a short distance upward, and the temperature can already drop dramatically. Stretch that difference across day and night, across open plains and cooling ground, and you get a world where thermal contrast is not just part of the environment, it is one of the main forces shaping it. Mars can climb to temperatures a little above freezing in the right place at the right time, then plunge to brutal lows after dark. A world that cannot hold heat becomes a world built around imbalance, and imbalance is where motion begins. This is the first piece of the storm engine. Temperature differences create pressure differences. Pressure differences create moving air. Moving air creates weather. That part is familiar. What is unfamiliar is the form that weather takes when you remove almost everything wet from the system and leave behind a dry planet coated in ultrafine dust. Because Mars no longer runs on the kind of cycles we instinctively associate with weather, there is no active water cycle shaping the atmosphere the way it does on Earth. No rain belts, no warm ocean basins feeding huge rotating systems, no moisture-laden air masses rising, condensing, and falling again. Mars still has weather, but its weather is built around something else now. Dust. That is the point where most people still underestimate what they are looking at. Dust sounds passive. Dust sounds like residue, something left behind after the real story is over. On Mars, dust is not an afterthought. It is not scenery. It is not just debris waiting to be pushed around by wind. It is part of the machinery. In fact, without dust, the largest storms on Mars may never form at all. This is where the planet starts to feel less like a dead desert and more like a strange, damaged system that found a new way to function after losing the old one. Mars no longer has the thick atmosphere it once had. It no longer has stable running water shaping weather on a planetary scale. But what it does have is a surface covered in material fine enough, light enough, and thermally important enough to take over part of that role. The atmosphere itself may be too thin to move heat efficiently. The dust is another story. Dust can be lifted. Dust can stay suspended. Dust can absorb sunlight. Dust can warm the air around it. And once that begins, Mars stops behaving like a world where weather is merely happening above the ground. The ground itself starts joining in. That is why the paradox is only a paradox at first glance. Mars does not produce giant storms despite being thin, cold, and dry in the way we imagine. It produces them because those conditions created a new kind of climate logic. A harsher one, a simpler one, a system with fewer moving parts than Earth, but in some ways, a more dangerous feedback once it gets going. So the real question is no longer whether Mars has enough atmosphere to make storms. The real question is what happens when a planet with almost no water, terrible heat retention, and a sky full of dust starts using that dust as part of its weather engine. This is the point where the picture most people carry in their heads starts to fail. Because when people hear the phrase Martian dust storm, they tend to imagine something violent in the most obvious way. A wall of wind, sand blasting through metal, antennas snapping, vehicles tipping over. The kind of threat science fiction likes, because it is immediate, visible, and easy to understand. But Mars is more deceptive than that. A dust storm there is not mainly dangerous because it hits hard. It is dangerous because it stays. That distinction matters. On Earth, when we think about major storms, we usually think in terms of force, wind speed, wave height, pressure, impact, what gets torn apart, what gets flooded, what gets ripped loose and thrown. That instinct makes sense here because Earth's atmosphere is thick enough to push with real weight behind it. When a powerful storm moves across the planet, it carries mass with it. Air has heft. Water has heft. Structures fail because the environment is physically battering them. Mars is a different case. Yes, winds in a Martian dust storm can move quickly. They can reach speeds that sound impressive on paper. But the atmosphere is so thin that those numbers can mislead you. Fast air is not the same thing as forceful air if there is barely any air there to begin with. A storm on Mars is more like being brushed repeatedly by a thin moving skin than hit by the body of a hurricane. So no, this is not the kind of storm that simply knocks over spacecraft. It is not the kind of storm that destroys things in one dramatic burst and leaves behind a clean visual answer to the question of what happened. In that sense, Mars is almost more unsettling. The threat is less theatrical, less cinematic, less satisfying. It does not always break a machine in front of you. Sometimes it just keeps taking away what that machine needs to live. That is the real shift in how this world has to be understood. The danger is not mainly impact. It is attrition. Dust settles slowly. Light fades slowly. Power drains slowly. Heat control begins to fail slowly. Communication degrades. Margins narrow. And a system that looked stable a few days ago begins to enter a different kind of time. One ruled not by what it can do, but by how long it can keep doing it. That is a far colder kind of danger. A rover on Mars does not need to be flipped or shattered to be killed. It only needs to lose access to sunlight long enough. A layer of electrostatic dust settling on solar panels does not look dramatic. It looks almost trivial, but on a world where energy is already precious, where nights are hard, where temperatures swing brutally, and where every heater and battery cycle matters, that layer of dust can become the beginning of the end. This is why the planet is so easy to misunderstand from a distance. The storm does not announce its threat in the way a storm on Earth often does. It does not have to. By the time the danger becomes obvious, it may already be operating in the background, not as a single blow, but as a process, a dimming, a narrowing of options. And if that sounds less frightening than a wall of wind tearing metal apart, it should not, because systems are often more vulnerable to long pressure than sudden violence. A human being can react to an explosion. A machine can sometimes survive one shock. But a long loss of light, a long drop in power, a long interruption of contact, a long period of exposure to cold and dust and waiting, that is different. That gets into the logic of survival itself. Mars, in other words, does not usually attack with spectacle. It attacks with conditions. And once you see that clearly, the planet begins to look less like a barren place, with occasional bad weather, and more like a world whose real threat lies in how easily it can turn endurance into the central test of everything we send there. So before asking how storms on Mars become so large, it helps to correct the basic image first. Do not picture a storm that wins by striking harder than anything on Earth. Picture a storm that wins by refusing to leave, by darkening the sky, by coating every exposed surface in dust, and by turning time itself into part of the assault. That is the kind of danger Mars has been building toward all along. So if Mars does not threaten machines with raw force the way Earth does, then what exactly is it using instead? The answer is sitting everywhere on the planet. Dust. Not as scenery, not as residue, not as the dead remains of a world that used to matter. Dust on Mars is active. That is the mental shift the planet demands from us. On Earth, when we think about weather, we almost automatically think in terms of water. Water evaporates, rises, cools, condenses, falls, gathers, and begins again. Oceans store heat, clouds move it, rain redistributes it. Storms on Earth are inseparable from the behavior of moisture and the enormous thermal engine tied to it. Even in places that feel dry, the larger climate system is still being fed by water somewhere. Mars lost that kind of weather long ago. What it has now is something harsher and stranger. A world where the old hydrological logic has mostly vanished, but motion remains, heat remains, air remains, though barely. And spread across the surface, in staggering quantities, lies a material light enough, fine enough, and thermally important enough to take over part of the work that water once did. That material is dust. This is why it is not enough to say that Mars is dusty. That sounds descriptive. It sounds passive, as though the dust is just there, waiting to be moved around by more important forces. But on Mars, dust is one of the important forces. It changes how sunlight is handled. It changes how heat is distributed. It changes what the atmosphere can do. And once enough of it rises, it begins to change what kind of storm the planet is capable of building. That is the hidden machinery. The atmosphere of Mars, by itself, is too thin to move heat around efficiently on a planetary scale, the way Earth does. That thinness is one reason the planet swings so violently between warmer daylight and brutal nighttime cold. But the dust behaves differently. Dust does not simply let sunlight pass through. Dust absorbs it, holds it, re-radiates it. A sky with enough suspended dust is no longer just a transparent layer above the ground. It becomes part of the planet's thermal system, and that matters because a climate does not need to look like Earth's in order to become dynamic. It only needs a way to move energy unevenly through the system. Mars has one. A dusty sky changes the balance between surface and air. Instead of sunlight mostly warming the ground and the ground then interacting with the atmosphere in a more limited way, airborne dust can start intercepting that energy directly. It heats the air where it hangs. It changes where warmth sits. It changes how quickly different layers of the atmosphere rise or cool. In other words, the moment dust becomes part of the air rather than just part of the ground, the rules begin to shift. This is why the largest storms on Mars do not come from wind alone. Wind matters, of course. Nothing starts without motion, but wind is only the beginning. The deeper process is that once dust enters the atmosphere, it starts helping the atmosphere become better at building the very conditions that keep dust aloft. Mars is not just blowing material around. It is, under the right conditions, creating a feedback between the surface, the sky, and the movement of heat itself. That is a very different statement. It means the planet is not merely suffering dust storms as side effects of being dry. It is using dryness to produce a new kind of weather. A weather system that no longer depends on oceans. A weather system that no longer depends on rain. A weather system that has made suspended mineral particles part of its engine. There is something almost counterintuitive about that. Dust sounds too small, too lifeless, too simple to carry that much importance. But planets do not care what sounds important to us. They care about physics. If a world is covered in fine material, receives sunlight, experiences strong thermal contrast, and has just enough atmosphere to lift and keep that material moving, then even something as humble as dust can become climatically decisive. And on Mars, it did. This is also why the planet should not be thought of as merely dormant. Dead worlds are easy to imagine because they feel conceptually simple. No water, little air, almost no life. And so the mind labels them finished. But Mars is not finished. It is stripped down. It is what a climate looks like after much of the buffering complexity has been taken away. The result is not calm in the way we usually mean calm. It is exposure. A rawer interaction between surface, air, temperature, and suspended matter. That is why the dust cycle matters so much. Without it, Mars might still be windy. It might still be cold. It might still have local weather. But the truly large storms, the ones that darken the sky and expand into something closer to a planetary condition, likely depend on dust not just being present, but being thermally involved. The atmosphere is too thin to be the whole story. The dust supplies the missing leverage. So, when we say Mars runs on dust now, that is not a poetic line. It is almost a mechanical description. Dust is one of the ways the planet compensates for what it lost, not by becoming habitable again, not by recovering its old climate, but by evolving into a different kind of world, one where the sky and the ground are tied together by particles small enough to float and important enough to change everything. Which leads to the next question. If dust is so central to the system, how does enough of it get off the ground in the first place? Because that is the step where a dusty world begins turning into a storm-making world. To understand how Mars builds storms this large, you have to start with a simpler question. How does the dust get into the air at all? That sounds obvious at first. Wind picks it up. End of story. But Mars is not that straightforward. In fact, one of the stranger parts of this whole system is that Martian dust is not especially easy to lift in the first place. The planet is covered in it, yes, but covering a surface with fine dust is not the same as making that dust ready to leap into the atmosphere whenever a breeze passes by. If anything, the opposite is often true. Very small particles can cling to each other surprisingly well. On Mars, many of those grains behave almost like staticky powder. They are fine, slightly cohesive, and stubborn in a way that works against the simple idea of wind just scooping them up directly. So before Mars can fill its sky with dust, it first has to solve a mechanical problem. It has to get the surface moving. There are a few ways this happens. The most visually dramatic one is the dust devil. Dust devils on Mars are not rare curiosities. The planet gets thousands of them, especially during the Martian spring and summer. The basic setup is familiar enough. Sunlight warms the ground. Air close to that ground warms too, becomes buoyant, and starts to rise. Cooler air nearby rushes in to replace it. Under the right conditions, that movement begins to rotate. A narrow spinning column forms. Then it stretches upward, sometimes widening, sometimes tightening, and begins walking across the landscape as though the ground itself has started to breathe in spirals. On Earth, dust devils can be impressive. On Mars, they can be enormous. Some can grow hundreds of meters wide and several kilometers high. Most are smaller than that, but the point is not just their size. The point is what they do as they move. They rake across the surface, suck dust upward, and leave behind trails of suspended material in the atmosphere. Not enough to create a global storm on their own, not even close, but enough to matter. Enough to darken the sky a little, enough to build background haze, enough to seed the air with dust that was not there before. That background haze is important because big systems rarely begin with a single dramatic event. More often, they begin with accumulation. Mars is no different. Dust devils help maintain a low but persistent burden of dust in the atmosphere. They are one of the ways the planet keeps the system primed. But for all their visual appeal, dust devils are not the main workhorse. The more important process is quieter, less cinematic, and much easier to overlook. It is called saltation. If dust devils are the obvious face of Martian dust lifting, saltation is the hidden hand. And the logic of it is wonderfully strange. The finest particles on Mars are often the hardest to move directly because they stick together so well. Larger grains, by contrast, are easier for the wind to push. That sounds backward until you remember that cohesion matters just as much as weight does. A bigger grain may be heavier, but if it is less tightly bound to the surface than a cluster of finer dust, then it can be the first thing the wind manages to set in motion. So a gust moves the larger grains first. They do not stay suspended for long. They are too heavy for that. Instead, they hop. They lift a short distance, travel, and then crash back into the ground. And those impacts do something the wind alone struggles to do. They transfer momentum into the finer dust resting on the surface. Tiny collisions, tiny bursts of force, again and again, enough to break cohesion, enough to free lighter particles and send them upward. That is saltation. The wind does not simply lift the most important dust itself. It recruits bigger grains to do the job for it. Once you see that, Mars starts to feel even more mechanical than before. The storm engine is not just driven by temperature and air. It is driven by impacts, by countless miniature collisions across a dry planetary crust, by grains knocking other grains loose, by a world using its own surface as a launch system. And once the finer dust gets up, another difference between Mars and Earth starts to matter. Mars has lower gravity. That does not sound like much in a sentence, but in the atmosphere it changes the rhythm of the whole story. Dust that would fall out more quickly on Earth can remain suspended on Mars for a very long time. Not minutes, not just hours, but in some cases, weeks or even months. That gives the planet something incredibly valuable if it wants to build larger storms. Persistence. A particle lifted today does not have to stop mattering today. It can stay aloft. It can keep absorbing sunlight. It can continue interacting with the atmosphere. It can become part of the next stage of the system. This is why the dust lifting problem is so important. Once enough material is airborne, Mars is no longer dealing with isolated surface motion. It is building atmospheric memory. The sky begins to retain traces of what the surface has already done. Yesterday's lifting helps shape today's heating. Today's heating helps shape tomorrow's wind. And from that point on, the planet becomes easier to tip. That is what makes these early processes so consequential. Dust devils and saltation are not the storm in its final form. They are the setup, the priming phase, the part where Mars quietly solves the problem of taking a dry, cohesive surface and feeding enough of it into the sky that the larger engine can start. So when people imagine a giant Martian dust storm, they often picture the end state first, the darkened atmosphere, the lost horizon, the global scale. But the real beginning is smaller than that. A warm surface, a spinning column, a gust across dusty ground, larger grains hopping, finer grains breaking free, a sky that grows just a little thicker than it was before. That is how the process starts. And once enough dust is hanging there above the planet, Mars can begin doing the part that makes everything more dangerous. It can start turning dust into heat. Once enough dust is in the air, Mars crosses a line. Before that point, the dust is mostly a consequence. Wind moved it, vortices lifted it, grains collided and knocked finer particles loose. The atmosphere is responding to the surface. But after that point, the relationship begins to reverse. The dust is no longer just something the atmosphere carries. It starts changing the atmosphere itself. That is the moment the entire problem becomes more serious. Because the most dangerous storms on Mars are not built by motion alone. They are built by feedback. Dust rises, yes, but what matters next is what that dust does while it remains suspended. And what it does is quietly powerful. It collects sunlight. That sounds simple, almost too simple, but it changes everything. The atmosphere of Mars is thin. By itself, it is not especially good at storing or moving heat. A lot of sunlight passes through it with relatively little interaction. But airborne dust is different. Dust grains intercept that light. They absorb energy that otherwise would have gone farther down, often toward the ground. Then, instead of holding that energy forever, they release it gradually into the air around them. In effect, the sky begins to warm from within. That is the transition that matters. A dusty atmosphere is not just darker, it is thermally different. And once the air begins warming at altitude, rather than only near the ground, the motion of the atmosphere changes with it. Warm air rises. That principle does not stop being true on Mars just because the air is thin. In fact, once enough of the atmosphere is being heated by suspended dust, rising motion can start happening on scales much larger than the little columns that created dust devils earlier. Now you are no longer dealing with scattered local lifting. You are dealing with an air mass that wants to climb. And when an air mass rises, something has to replace it. That replacement comes from the sides. Nearby air is drawn inward. New winds begin feeding the region. But here is where the system becomes dangerous in a specifically Martian way. Those incoming winds do not just fill empty space. They also sweep across the dusty surface below. They generate more saltation, more grains hop, more fine particles are knocked free, more dust enters the atmosphere. And once that new dust is airborne, it too begins absorbing sunlight, warming the air, and driving more rising motion. What began as lifting has become amplification. That is the core of the engine. Dust warms air. Warm air rise. Rising air draws in more wind. More wind lifts more dust. More dust warms more air. And around it goes. This is why it is not enough to describe a large Martian storm as merely wind picking up dust. That is only the visible surface of the process. The deeper truth is that the storm is building a relationship between heat and motion. Dust gives the atmosphere a way to trap and redistribute energy more effectively than the thin air could do alone. The atmosphere, in turn, gives the dust a way to remain aloft and to keep spreading. Each part strengthens the other. Mars has, in effect, found a way to turn suspended mineral particles into weather fuel, and that is the point where the planet stops feeling like a barren desert with occasional outbursts and starts feeling like a system with its own strange logic. Because on Earth, the major weather engines we fear most are fed by heat and moisture moving through an atmosphere thick enough to sustain them. On Mars, the atmosphere is too weak for that kind of engine, so the planet uses another route. It lets dust become the medium through which sunlight is captured and instability grows. That makes the storms feel almost improvised, as though Mars is building them out of leftovers, out of a ruined climate, out of the remains of a thicker, wetter world that no longer exists. But physics does not care whether a system looks elegant to us. It only cares whether the pieces can reinforce each other strongly enough to keep the loop going. On Mars, they can. Not always, not everywhere, not indefinitely, but often enough to matter and powerfully enough to change the scale of the weather once it begins. This is also the point where local intuition starts to fail. If you stood on the surface and looked at a dusty sky, you might think of it as a visibility problem, a bad day, an atmospheric nuisance. But higher up, in the structure of the air itself, a different story would already be unfolding. More heat is being retained aloft. Rising motion is becoming broader. Wind patterns are reorganizing. What looks like dust in the sky from below is, in another sense, the sky being reshaped. And because Mars has such low gravity and such a talent for keeping fine particles suspended, the system does not need to work quickly to become dangerous. It only needs to keep working. Hours matter. Days matter. If enough dust remains in the atmosphere long enough, each cycle strengthens the next. The atmosphere becomes more primed. The surface becomes easier to tap again. The storm begins to move from being a local event to being a regional condition. That is a very important distinction. A local event passes through a place. A regional condition starts taking over a world. The difference between those two things is not just size, it is structure. A small storm can be weather. A larger one can become part of the climate logic for a season. That is what Mars is capable of under the right circumstances. It can build not merely a temporary disturbance, but a state of atmospheric escalation. And there is something especially unnerving about how quiet the mechanism is. No oceans are roaring below. No thunderheads are piling upward with obvious menace. No rain bands are wrapping around a visible eye. Much of the process is diffuse. Dust lifted here, heating there, air rising over a broader area, wind feeding inward, more dust entering the loop. It does not always look dramatic in the way Earth teaches us drama should look, but dramatic is not the same as dangerous. By now, the planet has all the ingredients it needs to begin pushing beyond the local scale. The dust is airborne, the sunlight is being intercepted, the atmosphere is warming unevenly, the winds are being pulled into the system and returning to the surface with consequences. Mars has done more than start a storm. It has given the storm a way to feed itself, And once that happens, the next question is no longer whether a dust storm can form. The next question is how far this feedback can run before the whole planet begins to feel it. Once Mars has built that feedback, scale becomes the next problem, because the storm does not stay small just because it began small. At first, what you get may not seem like much. A dusty region, a darkened patch of sky, a local disturbance moving over open ground, something large enough to matter to a rover, maybe, but not yet something that feels planetary. And that is another way Mars can mislead you. The earliest stage of the system does not announce the size it may eventually reach. It starts like weather. Then, if conditions allow, it begins turning into something more like a season of atmospheric takeover. The first jump is from local to regional. Once enough dust is being cycled into the air, and enough uneven heating is building across the atmosphere, the storm no longer behaves like a contained event. It broadens. What was once limited to one area starts affecting neighboring air masses, neighboring winds, neighboring zones of lifting. Dust in one part of the atmosphere changes the thermal conditions in another. A system that began as a patch becomes a field, and Mars has a time of year when that escalation becomes much more likely. Its orbit is not perfectly circular. That matters because there are periods when the planet is closer to the Sun, and during the southern hemisphere, spring and summer, Mars as a whole reaches its warmest seasonal state. It is not warm by Earth standards, of course, but that is not the point. The point is contrast, relative warming. Enough extra energy in the system to make dust lifting and atmospheric feedback easier to sustain. That seems to be one of the windows when the planet becomes more vulnerable to runaway dust activity. And this part is important. The regional storms do not appear entirely random. They recur with a regularity that makes coincidence feel like too weak an explanation. Year after year, once the season is right, Mars begins behaving as though a threshold has been crossed. Storms form, dust loads build, systems enlarge, some merge, some reinforce one another. The planet does not look chaotic in the simple sense. It looks cyclical, structured, as though there is a larger rhythm in the dust engine that we can observe clearly, even if we still do not fully understand it. This is where the next escalation begins. Regional storms can merge into storms the size of continents. That alone should be enough to change how Mars is imagined. A continent-sized storm on a world with such a thin atmosphere already sounds like the sort of thing that ought not to exist. And yet, these larger systems show up often enough that they cannot be treated as freak accidents. Once the season turns favorable, Mars seems capable of building them with something close to clockwork regularity, not because every step is understood, but because the pattern is hard to ignore. And if the story ended there, Mars would already be one of the strangest weather worlds in the solar system. But it does not end there, because there is one level above the continent-sized storms, the global ones. This is the point where the mystery deepens instead of resolving. Scientists have a decent handle on many parts of the lower ladder. They understand that Mars lost its thick atmosphere. They understand that strong temperature swings can drive winds. They understand that dust devils help keep background dust in the sky. They understand saltation. They understand that airborne dust can absorb sunlight, warm the atmosphere, and reinforce further lifting. Those pieces fit together well enough to explain why Mars is capable of building serious dust systems. But the final jump is another matter. Why do some cycles produce storms so large they spread across the entire planet? That is still not fully clear. And that uncertainty matters because it marks the line between knowing an engine exists and fully understanding when it will reach its maximum setting. The largest storms on Mars tend to appear roughly once every 3 Martian years, or about every 5.5 Earth years. That is regular enough to tell us there is some deeper rhythm involved, but it is also irregular enough to resist easy explanation. The timing seems too short for very long orbital cycles of the kind that shape climates over tens of thousands of years. So whatever is driving this upper threshold appears to belong to the dust system itself, or to some seasonal or atmospheric interaction folded into it. One possibility is that the dust cycle needs time to recover, to restock the material or conditions that make a true planet-encircling storm possible. Another is that the regional and continental systems have to align in a particular way before the entire atmosphere tips over into the global state. There may be combinations of seasonal timing, surface dust availability, and atmospheric loading that have to line up closely enough before the whole machine runs at full scale. But that is still, to a meaningful degree, an open question. And that is what makes the global storms feel different from the lower stages. They are not just bigger, they sit at the edge of what we can describe confidently. That edge matters. It means that even now, With orbiters, landers, decades of observation, and a much clearer picture of Martian climate than earlier generations ever had, the planet still keeps one of its most consequential weather transitions partly hidden. We can watch the system climb. We can identify the season of danger. We can observe the aftermath. But the exact trigger that turns a very large storm into a world-swallowing one remains frustratingly incomplete, which is unsettling for a simple reason. Mystery at small scale is tolerable. Mystery at planetary scale is something else. Because once Mars reaches that top level, the question is no longer how strange the weather is. The question becomes what survives underneath it. A global dust storm on Mars does not need to tear a machine apart to destroy it. It only needs to take away the conditions that machine depends on. That is the point where the scale of the problem becomes real. Up to here, it is still possible to hear this story as a strange piece of planetary weather. A thin atmosphere, dust in the air, a climate system built from unlikely ingredients. Interesting, yes. Unusual, certainly. But still, to some extent, abstract. The global storms change that. Because once Mars reaches that level, the storm stops being just a feature of the environment and becomes a direct test of whether technology can continue functioning inside it. And the first thing it attacks is light. Scientists use something called aerosol optical depth, or AOD, to measure how much sunlight is being blocked, scattered, or absorbed by particles in the atmosphere. On Mars, under more ordinary conditions, the AOD is usually around 0.5. That is a workable sky, not perfectly clear, but clear enough that solar-powered systems can still function. For rovers and landers that rely on sunlight to charge batteries, the atmosphere can be dusty without becoming fatal. But the margins are not huge. Once the AOD climbs high enough, the available light begins to collapse. An AOD of less than about 2 is needed before solar-powered missions like Opportunity or Insight can reliably charge their onboard batteries. That is already a reminder of how narrow the energy budget can be on Mars. The system does not need complete darkness to become dangerous. It only needs enough dimming, for long enough, to break the balance between what a machine takes in and what it spends to stay alive. And then come the global storms. These storms do not push the AOD from 0.5 to 1, or from 1 to 2. They push it to 9, sometimes 11. That is not just a dusty day. That is a sky approaching total light failure. For comparison, thick wildfire smoke on Earth, the kind that can make noon look like evening, might reach an AOD of 7. The largest Martian storms exceed even that. The sunlight does not simply weaken, it is nearly smothered. This is where the planet stops feeling remote and starts feeling cruelly practical. A rover does not experience that storm as spectacle, it experiences it as starvation. Power drops, charging slows, then stops. Heaters become uncertain, communications windows narrow. The line between survival mode and irreversible decline starts getting thinner by the hour. That is what happened to Opportunity. By 2018, Opportunity had already outlived what anyone originally expected from it. It had survived for years on a world that gives machines very little forgiveness. Then, a planet-encircling dust storm arrived. The atmosphere thickened with suspended dust. Light levels crashed. Its solar panels could no longer collect enough energy to keep the rover alive in any meaningful long-term way. Opportunity entered hibernation mode, the mechanical equivalent of waiting in darkness and hoping conditions would improve before the internal losses became too large. They did not. Without enough power to keep essential onboard heaters running, the extreme day-night temperature swings on Mars are believed to have caused something critical to fail, and when the storm passed, Opportunity never woke up. That is one of the most important emotional truths in this whole story. Opportunity was not crushed. It was not blown over. It was not smashed by a physical strike. It was slowly denied what it needed to remain itself. That is a distinctly Martian form of death, and it is exactly why these storms matter so much for every future machine we imagine sending there. Because even when the wind is not physically strong enough to knock a structure down, the storm can still erase the energy economy that structure depends on. Dust deposition on solar panels, sustained dimming of the sky, thermal stress after power loss, and long periods where systems are forced into minimal operation can be just as lethal as impact, sometimes more so. Even machines that are not primarily dependent on solar power are not simply safe. Take Curiosity, for example. A rover with an onboard nuclear power source is far less vulnerable to light loss than a solar-powered one. It does not die as easily from a darkened sky, but global storms still matter. The dust clouds can become thick enough to interfere with communication between the surface and orbit. And that means a rover may remain alive, warm, and mechanically capable, yet still be forced into a period of waiting because the link between Mars and the people trying to guide it from Earth has been weakened or cut off. The storm does not have to kill every machine to dominate operations. Sometimes it only has to isolate them. That, too, is a form of power. A storm that can reduce an active mission to silence, even temporarily, is not just weather. It is a systems-level event. It changes what science can be done, what commands can be sent, what risks can be managed, and what decisions can even be made in time. It forces patience where control would normally exist, and the surface is not the only place Mars feels the storm. Orbit is affected too. This is one of the less intuitive consequences, but in some ways one of the most revealing. When huge amounts of dust remain suspended in the atmosphere and absorb sunlight, they do not simply make the sky darker below, they also warm the atmosphere enough to make it expand. That expansion pushes the upper atmosphere higher into space, farther than it would normally reach. And once it does, some satellites suddenly find themselves moving through a region with more drag than expected. They have to burn precious fuel to correct their paths and avoid losing altitude. A storm on the ground becomes a threat to hardware above it. The whole planetary system starts feeling the disturbance at once. That is what makes the global storms so much larger than their visuals. They are not just walls of dust. They are episodes in which Mars begins altering the operating conditions of everything we have placed around and upon it. Surface power becomes uncertain. Surface communication becomes uncertain. Orbital stability becomes more expensive. Mission planning becomes reactive. Time starts being measured not in new progress, but in how long the storm can hold the initiative. And that has a direct meaning for the future. Because every rover lost this way is a warning. Every blackout in communication is a warning. Every orbital correction forced by atmospheric swelling is a warning. They all point toward the same conclusion. Mars is not merely a difficult place to reach. It is a difficult place to keep working on. And if the planet can already do this to robots built by specialists on Earth, then the question waiting beyond them is obvious. What, exactly, would it demand from humans trying to live there? If that is what these storms can do to robots, then the question hanging over the whole story becomes unavoidable. What would they do to us? Because the moment human beings stop visiting Mars in imagination and start trying to stay there in reality, the storm problem changes categories. It is no longer just a challenge for remote machines, or a complication for mission planners, or an atmospheric curiosity studied from orbit. It becomes part of the basic contract between people and the planet, a condition of life. Something every habitat, every power system, every communications link, every rescue plan, and every margin of error would have to be built around from the start. And Mars is not a world that allows much slack. A settlement powered mainly by sunlight would be living under a very narrow form of confidence. It would work until it did not. It would be efficient until a season of dust turned efficiency into fragility. Because a global storm on Mars is not just a few bad days of low visibility. It can mean weeks of reduced light. Weeks in which your main source of incoming energy becomes unreliable. Weeks in which the outside world is still there physically, but less available to you in every way that matters. You may still have habitat pressure. You may still have stored oxygen. You may still have heat, if you designed well enough. But the whole settlement would enter a different state of existence. A waiting state. A conservation state. A state where every system has to justify its continued operation against the energy it consumes. That is not science fiction drama. That is simply what happens when survival depends on maintaining internal order, while the environment outside has turned against your assumptions. And on Mars, assumptions die quickly. Humans do not do well in deep cold. We do not do well in isolation. We do not do especially well when communication becomes uncertain, and external help, even if it exists, is not something that can arrive quickly. A storm of this kind would put all three pressures into the same space. A habitat might remain alive and functional, but its relationship to the outside world would tighten. You would not want to depend on a power model with no redundancy. You would not want life support that only works comfortably when the skies are cooperative. You would not want to discover, in the middle of a global storm, that your settlement was designed more for arriving than for enduring. That may be the deepest lesson Mars keeps trying to teach. Reaching a planet and living on it are not the same problem. Landing is dramatic, staying is repetitive. Landing can be built around a moment. Staying has to survive systems, seasons, and failure. And dust storms force that distinction out into the open. They strip away the romance of settlement and ask a simpler question. If the sky goes dark, The temperature keeps swinging, the satellites become harder to reach, and no one can come help you soon. What still works? That is the real standard. Not whether a habitat looks convincing in a concept painting. Not whether a mission lands on schedule. Not whether the first footprint makes the news. What matters is whether the system remains alive when Mars stops being generous. And yet, for all their scale, for all their power over machines and plans and human imagination, these storms do not last forever. That is another one of the planet's strange mercies. The same mechanism that allows a global dust storm to grow eventually begins to undermine it. Dust lifted into the atmosphere absorbs sunlight, warms the air, and helps drive the larger rising motions that pull in more wind and keep the cycle going. But that process depends on enough sunlight still reaching the lower system to sustain the thermal differences that started everything. As the atmosphere becomes loaded with more and more dust, more of that sunlight is intercepted high above the ground. The surface below receives less and less energy. Eventually, the ground is no longer being warmed strongly enough to maintain the upwelling motions that continue feeding fresh dust into the sky. The engine starts losing its fuel source. The storm has not been defeated by an outside force. It has begun starving itself. This is one of the most elegant parts of the whole system. Mars builds the storm through amplification. Then the storm succeeds so completely that it begins shutting down the very conditions that let it live. Dust blocks light. Less light reaches the ground. Less ground heating means weaker rising air. Weaker rising air means less new dust lifted. Less new dust means the system slowly runs out of momentum. And once that decline begins, the planet starts returning to itself. Not all at once, not dramatically, more like a long exhale. The sky thins. Light comes back in stages. The horizon returns. Signals recover. Any rover still alive beneath the dust begins, in a sense, to re-enter the world. This is the part where Mars becomes deceptive again. Because after a storm passes, the planet can look quiet in the old way. The surface stretches out. The atmosphere clears enough. The machinery of crisis folds back into the background. If you arrived after the fact, if you only saw the red plains and the open distance and the absence of visible violence, you might once again mistake the place for dead stillness. But that is no longer the right way to see it. Not after everything the storm has revealed. Mars is not still because nothing happens there. It is still between episodes, between thresholds, between cycles in which the planet gathers enough heat, enough dust, enough imbalance, and enough time to remind anything living or working on its surface who is actually in charge. That is why the ending of the storm is not really an ending at all. It is a pause. A rover that survives may wake again. A habitat may stabilize. Communications may return. Science may resume. The red world may once more look empty and patient beneath a thin, cold sky. But the conditions that made the storm possible have not gone away. The dust is still there. The temperature swings are still there. The thin atmosphere is still there. The strange climate logic of Mars is still there. And somewhere ahead, whether in years or in the next vulnerable season, the cycle will begin again. A little wind, a little lifted dust, a sky that grows slightly darker than it was, then warmer air aloft, then more motion, then a larger field of instability. And if enough of the planet lines up in the right way, the whole machine will run once more. That is the truth hidden behind the first impression of Mars. It is not a dead world that occasionally surprises itself. It is a world with a functioning climate, just not one built from the ingredients we are used to. A climate stripped down to dust, sunlight, thin air, and imbalance. A climate capable of becoming global. A climate that can outweigh machines, challenge settlements, and force every future human plan there to answer a hard question before it can become real. Can you survive the planet when the planet decides to close in? Because that, more than rockets, more than landings, more than the symbolism of setting foot on another world, is what Mars will ask in the end. Not whether we can get there, whether we can remain there when the sky goes dark, and when the dust finally falls, and the light returns, and the horizon opens again, Mars will look calm. It will look almost silent. But it is not silent. It is only between storms.